recording on this. Okay, so the problem tested on the macro PChem, and the first question is about ideal gas. This is a Z value is a unity. This is what we call the compressibility, which is true for the real gas. And this one you can solve in a various ways. Hopefully, if you remember, okay, oh, this is not good. Okay, if you remember the Z value is 1 is an ideal when the Z value is smaller than 1, and that's an attractive. And the Z value is positive or plus 1, and that's a repulsive. If you remember that will be great. If not, then you have to probably, I hope you guys can remember that Z is essentially the measured volume over a volume that is supposed to be. So when there's an attractive interaction, this Vm, the real volume, is smaller than no interaction volume. When there is a repulsive interaction, the measured volume is actually higher than the one that is with an ideal gas volume. Okay, so in the same sense, this is a case where attractive interaction A is positive for van der Waals gas, and this is for the negative for the van der Waals gas. So okay, so I get this one for the real gases, but now I start to see the argument about the pressures, and the high pressure means that you are bringing the molecule closer together, right? The low pressure, you are moving the molecules apart, right? So probably this is you might remember this interaction potential as a function of distance between two molecules R, and this is what we call attractive. Eventually, at the pressure that is close to 0 and no interaction, that means an ideal. That's what I think that we also covered. But typically, when you have the molecule farther apart, instead of enforcing them to bump into each other, they have an attractive interaction. Sometimes they are attractive enough, be attractive enough to condensate into a liquid. So high pressure means repulsive. So repulsive, high pressure. Eventually, right? So high pressure, repulsive. And low pressure, Z is 1. So this will be my first choice for that answer. Okay, so the second one is, which of the isotherm is experimentally observed near the critical temperature? Okay, I think I remember showing you a video about van der Waals and working with ohms in the competing for the absolute zero. He bring out the concept about the critical temperature. I didn't go too much in the detail before at that time, but this is a concept. If you plot the van der Waals gas, this one actually go up and down. This is one of the flaws in the van der Waals gas, pressure versus volume. But this kind of the curvature change, you can put the straight line that this is a Maxwell construction, where this is where this is a low volume, so this is a liquid, volume for liquid, and this is a volume for gas. This is where volume for liquid and the gas can coexist, and so the liquid to gas condensation can occur at the temperature lower than critical temperature. At the temperature higher than critical temperature, what's going to happen is it's just like this, without having these wiggly lines going up and down. So this is a temperature higher than critical temperature. And this is what we call the supercritical temperature. Supercritical CO2 is an example. So therefore, it's just before they oscillate, and this is the wet temperature is at critical temperature. So therefore, from the van der Waals gas relationship that we learned, this is at critical temperature. That's what you see. Okay, going to number 3. So let's read the problem. Enthalpy of a water at 1 bar is changing such and such and showing in the graph. So what I see is H versus T. And there is a graph showing up there. And which graph represent constant pressure, heat capacity. So constant pressure, heat capacity is a CP. And this one is essentially want you to know that CP is a slope, temperature slope of enthalpy at constant pressure. So what I need is there's a slope. And you can see that this one is a higher slope than this is a lower slope. And this is a constant slope regardless of temperature where you are, is a constant slope. So constant CP, and I can see that this one is a larger value. So this is a larger value, this is a smaller value, right? So constant CP. And then this is a slope, which is a ill-defined, and in the experiment it's shown up as a peak. So that's what there is. But I think the problem maker did not want to show anything that mathematically not defined well, so we just show the two discontinuous line, and there's a discontinuity in between. So that's the answer for this one. Talking about PV diagram, this is a PV diagram for the reversible expansion. Okay, so so this is an isotherm, this is an adiabatic expansion, and which one describe relative amount of the work done. So this is actually what they're trying to say is, this is a little bit ambiguous, but relative work magnitude is what they're trying to say. I think in their work is here is essentially work magnitude, and this is we're talking about reversible. So from the PV curve, as you remember that work in general is P external dV, right? And work reversible is P dV internal, and then changing volume from volume 1 to volume 2. So expansion wise, your work is negative, but it is always the area under the curve. If this is a P versus V, volume 1 to volume 2, that's the area under the curve, and that's the magnitude of the work. Right? And as you can see, the adiabatic work is smaller than isothermal work expansion. So adiabatic reversible expansion does less work. So I would say the B is the correct answer. Okay, so I think it's this one kind of going to the recap on what we learned so far. The next one is about let's look at the problem. Sometimes they give you this system. Let's say the N is 1 mole. So the volume that you are dealing with here is per mole basis volume, and this is a temperature. And then this gas is isothermally and reversibly expand. Calculate the work done on the gas. Okay. Calculate the work done on the gas. Okay, this is wow. Okay, calculate the work done by the gas. I think that's a better problem to solve it, because this is my system, right? This is my system, and they just want you to calculate the work. But it is, they say, is a reversible, so I can use this pressure expression for my one, and it is also isothermal. So what I need to do is, okay, so this is a problem that I need to solve, and then work reversible is minus P over dV. And because it's a molar volume, I will just call the dVm. Okay, and then we are talking about 2.5 liter to 4.00 liters. Okay, and the pressure, you have to integrate them over here, right? So then, using this is the P, which is an RT, 1 over Vm, Vm squared to the B. So I am going to put this equation inside to do the first one. So RT, natural log, Vm, 4.0, 2.5 plus, okay, so this is the whole thing is a negative, and then the RT integral RTP integral Vm square Vm and 2.5 4.0. Okay, so let's have a look at this. The B value is a virial constant, and the virial constant shown up here is a negative. Okay, so that means that this pressure value, this is a negative value, so the pressure is lower. Pressure is lower, that means that the work will be less than, I guess, ideal gas volumes. Okay, so this is what you normally known as an ideal gas kind of the amount of the work. Okay, so this whole thing with a negative sign. So that's how I want to solve it. Okay, so there's a couple of tricky part because of we know the gas constant RT. So let me use the space over here. Work reversible is minus 8.314 multiplied by 300 natural log 4.0 2.5. And this one itself is essentially what you known as work reversible ideal gas. Okay, so let's calculate the first term and the second term later. Okay, the first term here is minus 1170 joules. Okay, so you already know that that's the work amount that is being done, and the magnitude is 1170, and this is you can see that this is an ideal, right? And this cannot be the one. And I know that this value should be the magnitude to be smaller than 1170, so it could be either A or B. So if you do not want to do the integration of the second part, your guess is coming down to 3 choices, but A or B will be your more reasonable choices. Okay, so then what I need to do is I need to do the second integration. So the second integration, work reversible, which is a minus And this is an RTB, and you see the B is done in the liter per mole, and this is done in the liter per mole. So it's when you do the integration of 1 over x to the dx, that's a minus 1 over x plus c. So therefore, you will have a minus with a minus sign, so that's a plus. And then RT, which is the same as this one, 314, 300. And the B value, I will just retaining as they are, because minus 21.7, 10 to the minus 3. Knowing that this is a liter per mole, and now I need to do the 4.0 minus 2.5, and this is essentially in the unit of mole per liter, right? So these two units are canceled out, and these units are canceled out, so I don't have to worry about those units conversions. And so I plug those numbers, and then this number itself is negative, so it is minus 0.15 mole per liter, and if you multiply all of them, then you will find out that work reversible is 8.11 and then joule. Okay, so this is a first one is a minus 1170 and plus that, and you will get to see the one. The closest one is an A. Okay, so that's how we can do. All right, let's move on to the second problem. And this is a protein myoglobin at this temperature, and this is where the native and the denatured protein goes back and forth, and they give you the delta H and the delta Cp values. And this is an equation that I kind of hear showing up here. Delta H at different temperature is delta H at certain temperature with temperature differences multiplied by delta Cp as standard. Okay, so we want us to know delta. Let's do this one more time. T2 is delta H T1 plus delta Cp. This is the one probably I didn't emphasize much, but it appears quite a few times in standard tests. So it's good to know this relationship at delta H at different temperatures. And so now asking us, T2 is 323, T1 is 343, and okay, and then the Cp is a plus kilojoule, and the T2 is 323 minus 343. So I guess that's a minus 10 Kelvin. And using this, so you will get this number. What used to be delta H is 520, and this number should be smaller than 520. Okay, so what's this number now? Okay, so this is this number itself is 520 kilojoule per mole plus 12 kilojoule per mole Kelvin, right? Per mole Kelvin, so mole Kelvin, and now the difference is minus 10. So this one itself is minus 120 kilojoule per mole. So therefore, your okay, 520. I think that there's something wrong here. 423. This is not 10. This is 20. Okay, this is 20. So therefore, this is 240. So minus 240 kilojoule per mole. Okay, so delta T is actually minus 20. So therefore, the answer is plus 280 kilojoules. Okay, number 3 is this third one, essentially asking us to calculate this. And for this, I guess the iron oxide reduction using coke or carbon source to making this CO2 gas, and then we can reduce the ions. This is what's happening in the steel plant when they make this rust into the iron. The delta H at 300 Kelvin is such and such, and the delta S is such and such. So assuming no change in either quantity in temperature at which the reaction just becomes spontaneous. So what's important here is delta S. So delta T over T at transition. Yeah. Thank you for the comment. I was looking at the screen. Yes, the temperature difference is minus 20. That's right. So delta S is that, and this is coming from one of the things. ds is our original definition, reversible heat over T, and at transition, that heat reversible is delta H, and then we can put those numbers in. And so they give us the delta S is 270. So this is entropy of phase transition. I think that's why I made it this kind of the information that you can find in the textbook. That's a nice reminder for you guys. Okay, so this one is 279, and the temperature. And what was the delta H is 234 kilojoules. So that's the numbers, and that will give me the temperature is around 840 Kelvin. Okay, so that's about 1,000 Kelvin, and that's my definition or calculation. Okay, so this is the one that number 8. Number 8 is actually quite commonly shown up, and I didn't really clearly emphasize in my exams or maybe in my lectures, just for that. Do you remember that? So anything that defines the thermodynamic function that can be expressed as a combination of two dependent variables, and here is a Helmholtz energies, and this is known as a rubber elasticity, and L is how much stretching you have, and the temperature is just like the others. So it is an analog about dA. I don't know why this static is keep on happening here. I need to bring some. Okay, so then. Oh, okay. This is, I forgot the actual equations, but anyway, what I want to write here is this one was expressed in terms of two variables here. Just like I pick two variables, and then this is a length change, and this is a temperature change, and generically we can write thing as round A, round L, keeping temperature constant, round A, round T, keeping L constant. So that's just a expansion of what we said before. And then this one is telling me that this is a case for, that's a force times dL, and that's an entropy times dt. And so as far as stretching the rubber molecules in stretching the rubber-like sample. This is how the free energy is being defined. And then they wanted to essentially how to come about the Maxwell-like relationship is being done. So this is an F is that. So when you take an F and taking the other one, so we used to do the round L, so now round T, round, and L should be same as taking minus S, right? And taking this round, because I have done the T first, so now we can do the L over T, keeping the T constant. So that will be another Maxwell relationship that is given out, okay? So then this round F, round T over L is minus round S, round L over T. So where we are now, that's, yeah, so this is the one. A is the right answer. Okay, so far so good. Going on. Okay. So now there's another question about here. There is a azo-oxyanisole melts a near nematic liquid crystal which persists up to 409 Kelvin, assuming so this is a melting temperature, and then this is a temperature of 409. So if I graphically draw these cases, this is a temperature, you're heating it up, and that's a temperature of 391 Kelvin. That's your melting temperature, and we are talking about 409 Kelvin, which is above the melting temperature. And then they are essentially looking at the delta S issues, or S issues, and you start from the S naught, which is a zero entropy. So you remember this one goes up like this. You have to do a little quicker, so you have to go like this. And then at the transition, you are seeing the delta S changes, and you are seeing the continual rise. And as you might remember this equation up here, right? So that's an equation. So let me write the equation once more. And what that means is S at temperature is ST1 plus CP as a temperature over T, doing T1, T2, dt. So that was the original concept. We are starting from here 0 Kelvin and S naught, which is close to 0, and so that's the one. So the question is, assuming one solid phase, which of the following property must be measured in order to determine the entropy change, which is, I guess we are talking about now S409, starting from S naught and 0 to what is a 391 and T CP dt, and then the T and the delta H melting plus 391 to 409 CP T dt. Okay, so those are the one that I think I need it happen. So I need a delta H melt, I need a CP throughout all the temperature ranges. So 2 and the 4. So that's my answer. I'm not so sure that whether the other VM or volume changes, this has something to do with more the pressure related term, but I think that for now this is a right answer. If you have a better answer, let me know. But that's what I come up with an answer. Okay, so the plot the best represent number 10, best represent possible variation of delta G over the time as a closed system process involve only pressure volume work at constant temperature. So I guess ideal isothermal volume change work, and the pressure approach the equilibrium in the forward direction. So equilibrium means your delta G is 0, right? And then when they're moving forward, that means a spontaneous, right? And so that means the delta G was a negative in the beginning. So over the course of the time, you want this one to be negative, approaching the value to be 0, right? This is not approaching to the 0. That's not good. That's a positive, so that's not good. So B is the correct answer for this. Number 11, on the physiological condition, potassium ion will pass through the cell wall membrane until they essentially reach the equilibrium, right? Our bodies is constantly being in non-equilibrium state because we know that this is our cell, and high potassium concentration and the low potassium concentration, but we want actually pump the potassium to make a potassium concentration higher. In a perspective of the osmotic pressure, right? This is an equation that you might remember. And actually the focus is now on A, which is actually solvent. In this case is a water, right? If you think about the water here, they see the difference in the chemical potential. The water likes to go in, and because they have a more salty in here. So therefore the water permeates through until they reach the steady state, until their chemical potential is essentially the same. So my answer is a chemical potential of the potassium ions is in the same on both sides of the membrane. So does the water. So I think that my choices will be the D. So this is more like a concept question they give out to us. All right. Okay, so now let's go to the number 4. So this is a case where you are seeing this potassium pentachloride decompose into the 2 gas species, right? So if you think about it, the reaction forward is generating the more gases and so on. And then you can see that this is an endothermic reaction. And so what should if I want to be stored and I want this one to be more favored under the equilibrium conditions, I want exothermics. So, but I want the reactant to be favored in to shift it, right? This is a Richatel's principle, and to do this. So therefore, the lower temperature will be one that favor this. And if you're looking at this is an N is 1 and this is an N is 2 on this side. So by pressurizing this, you are pushing the equilibrium code this way. So that's on high pressure. This is a oh no, sorry. Anyone has a question? I got carried on. Okay. Endothermic. So endothermic means, I think I'm getting tired already. Endothermic means heat absorbing. So let me see. Heat absorbing. So endothermic. So if the reaction go backward, you need to go to lower temperature. I think I'm right. Okay. And then the pressurizing this. So this is a one. So therefore, the answer here is B. I hope you guys okay with me. Okay, so let me switch the comments. All right, so now let's look at this reaction. Hydrogen, deuterium gas, chemically pretty much the same gas. They kind of exchange bonds each other. They form the HD gas molecule, partially deuterated hydrogen. Hydrogen and chlorine make the HCl. There's a big chemical bond change, and there's a bond reaction and so on. So choose a set of the relationship that correspond to the standard enthalpy and entropy of the reaction, and then the equilibrium constant for the reaction. So if you're looking at the way the chemical differences between the first one, the number one, there is not much of the differences, right? So there's not much of the differences in between. So one other things that you can start to relate it is, remember the delta G is delta G naught plus RT ln K, and then equilibrium is 0. So therefore, I would say the ln K is minus RT delta G naught. Okay. So equilibrium constant is related to those two values. And as far as the gas is concerned, this is a two gas molecule generating the two gas. And we've been talking about throughout in my class that gas is much more chaotic. They have a highest entropy. So before and after, 2 moles of gas, 2 moles of gas, 2 moles of gas before and after. So therefore, the entropy changes for this is essentially virtually the same. And this is pretty small. And then if you're looking at the way that how this reaction can occur, the bond changes from H to D and D to HD. They are not chemically different. So I would say delta H is also close to 0. Okay, it's not so difficult, not so different. Whereas here is there's a heterogeneous bonding is being formed, and I would say this is a very exothermic to make this reaction more likely the spontaneous. So that's my guess. So to be able to make that, when do you remember the delta G is delta H minus T delta S for a constant temperature. So when this is a negative values. So the big negative that makes a big negative G, and then that makes the K values to go up pretty high. So therefore, my assessment here is the K2 value is smaller than K2 value is bigger than K1 value when their negative value is smaller than the 0 values here. So this will be my answer as far as I can make a guess. Okay, so number 14 is about the Claudius Claparian equation, and this is an equation that is from the Claparian equation. And then there's a obvious two assumptions. One is delta vaporization, volume change for the vaporization is the gas volume minus liquid volume, but we are going to neglect that. And once more, that's PRT. So this is usually the molar volume, so I just say the molar volume. So that's the one, and then this is a second assumption, number 1, and the number 2 is an ideal gas. The best vapor is an ideal gas. Okay. So once you have those two, the vapor is an ideal gas, partial molar volume is of liquid is negligible. No, not partial molar volume, just a molar volume of the liquid is negligible. Okay, so the 1 and 2 must be included. Yet I need to make third choices, and which is the following. So once you have those things combined, and then this one also, we are using the delta S vaporization is delta H vaporization over temperature. And so those are, if I use this equation, this one comes down to dP dt is delta H vaporization and RT square and the pressure. So when I do that, so then dP over P is RT square delta H vaporization dt. And we need to do the integration. And the one, if this is this could be temperature dependent, but we are taking this one as a constant temperature out, and so therefore we are talking about P2 or P1 is minus delta H vaporization over R with a negative sign, because integration about 1 over x squared is 1 over x. So this is a T2 minus T1. So that is a fact that delta H vaporization is constant over this temperature window that we want to do the integration over. So this is a 1, and the C is the correct answer. Okay, number 15 is actually pretty much Chem 2 problem. Let's do this. So the enthalpy change. Enthalpy is a state function, and they want us to know delta H for this particular reaction. And this is actually being bound by the way the reaction is written, right? So if this is the case, I'm looking at H2 here, I'm looking at H2 there. So what I can do now is I'm going to flip this. So H2 half O2 H2O. And then delta H for this one is minus 285. 285.8 kilojoule. And then I can see that H2O2 is here, but this constant is 2. So what I can do is this one I'm going to write as it is, but I'm going to multiply both sides by half. This one is okay, so negative changes. Right? So okay, so then by doing so, H2O half O2 becomes H2O2, and the delta H for this one is half of 196.1 kilojoule. Okay, so if you add them together, this is gone, and then H2O2, H2O2. That's the reaction that I want. And make sure the gas and the liquid is all corresponding correctly. So therefore, delta H value should be minus 285.8 plus half 196.1. And that's a 187.8 kilojoule. Just this one. Okay. Do you have any questions so far? Things are looking good. Johnny, Vanessa, everything is good? Okay. All right. This is another one that's showing here once more. And for at temperature of 290K. So this is a delta H naught at designated temperature, 298 Kelvin. And this is the value for that. And they want to calculate delta H at 500 Kelvin. So once again, this standard state was defined at 1 bar at designated temperature, and typically table was given at 298 Kelvin, and they wanted to calculate what about at different temperature, and that's 298 Kelvin, delta Cp, and then T2 minus T1, right? Saying that this is a T2 and this is a T1. So what's my value here? Minus 184.6 kilojoule plus minus 4.43 joule. So remember that there is a little tiny differences. And then 500 minus 298. And I will just multiply by 10 to the minus 3 to make it as a kilojoule on both sides. Okay, so by doing so, this side, the correction, delta Cp, is a minus 0.89 kilojoule. And that make it this value. The B is the correct answer. Minus 185.5 kilojoule. Okay, so that's an equation that I think that I didn't emphasize enough for the measuring or estimating the enthalpy at different temperatures for the designated temperature that we know from the table, and then this is how you can find the value at different temperatures. Okay, so now this is a phase diagram. This is a one component system, so I guess the C is 1, and you might remember C minus P plus 2, and this is the case 3 minus P, right, when C is 1. And so therefore maximum P is 3, which is a F equals 0. There's a F negative is not possible, and that's a one designated point. That means this is what we call the triple point. I hope you guys remember this one of the diagram of my. This is a water. This is a CO2, right? And also we were saying that if somebody draw like this is not possible. Probably they might have something like. If they draw it, probably it is something like that, and they just and this is allowed, whereas this one is not. So for example, this one is not allowed, and so phase diagram 1 is impossible because no more than 3 phases can coexist. That's the maximum degree of freedom. And here, okay. So if that's the case, that's the one. Okay. Number 18 is some concept that I didn't discuss with you, and so here I have to discuss. I hope I'm right on this kind of the scenarios. So if you look at the way, this is an energy of a different state. That's an energy diagram for A, and B is energy level of different state. And as you can see that this is the higher energy state is much more so here, higher energy state are more easily accessible, right? So therefore they can go back and forth, and then they have a much more higher entropy. So this is my understanding. Whereas energy-wise, they certainly prefer this, but entropy-wise, they want this kind of it's not degeneracy, but this multiple state, they can go hop back and forth, so they can have more favorable in entropically. So B is favorable by entropically, A is favored by energetically. Everything is go far. I have to call different name. The Johnny and the Vanessa answered that. So now, how Molly? How are you doing? Any questions? Number 18. I'm doing good. Okay. Well, what about the Rebecca? Good. Okay. So this is some of the concept, but I don't know. I'm not so sure whether I'm correct or not. But you might find different answers. Let me know. Okay. So let's keep on going on here. This is also what are the magnitude of contribution to the molar heat capacity of a nitrogen at 298 Kelvin, right? So we are talking about energies. Energies is a translational, which is pretty much like this, right? This is a translational energies. And then there is a vibrational energies, which has something to do with like this. And then there is a rotational energies, which is more like rotating things like that. And energy-wise, the biggest principal component is a translational energy. So the energy contribution from the translational is highest, and the vibrational comes next, and the rotational energy is really the smallest contribution to the total internal energy increases, and CV is round U over round T of a constant volume. Okay, so I think my answer is A. I also had looked at what is called the Wikipedia pages, and then looking at N2, the CP values, molar actually heat capacity, 29.0, 31.3, 38.0. So that's a 25 degrees C, and this is a 500 degrees C. This is 5,000 degrees C. The higher temperature you go, you start to have more contributions from the other things are much more significant, because the molecule vibrates and rotate. Those energies are high enough to contribute to the energies. So I think my answer is an A. Translational is the highest contribution, then vibrational, and the rotational comes the next, comes at the end. Okay, so we are getting close to something that we kind of discussed before. Let's look at the problem. Chloroform boils at 62 degrees C. Acetone boils at 56 degrees C. And if you mix half and half, and that boils at even higher temperature, right? So what's going on? The chloro, essentially this pretty much what that means is chloroform and the acetone, they attracted each other, and so it's more difficult to boil when the chloroform acetone has an attractive interaction. In other words, in the regular solution theory, the psi value is 0. Okay? So I cannot draw the boiling temperature concept, but I can certainly draw this diagram that was related to you before. This is 0. This is a PA star at the top, and I'm plotting PA versus composition XA, 0 to 1. And this is what is called the Raoult's law. And then when they have a positive interactions, and this is a This is where you have a, this is a PA equals PA star XA. That's a Rouse law, right? And this is these two cases where you have a psi value is positive, and that means a repulsive interactions. But when you have something looks like actually lower than this, and this is a case where your psi value is zero, smaller than 0 with a negative value, that means attractive interaction. And so let's say the system deviates from the Rouse law. So this is a Rouse law. And they deviate negatively, that's what it means. And the stronger interaction forces between chloroform and acetone. Right? So this is an answer for they have an interaction. And if you, this is also quite well-known relationship. I think that I want to emphasize here. So chloroform is a CHCl3, right? So this is a chloroform that looks like this. Is actually, you might want to know this. So this is because strong electronegativity. This one is actually positive delta. Okay. Whereas acetone, oxygen with the lone pairs, just like in water, you are having hydrogen bonding character. So hydrogen bonding is a quite strong bonding nature about this. So this, so therefore they have actually interaction is negative. They actually attracted to each other than the chloroform itself or the acetone itself. Actually, they like each other more. That's actually pretty good. Okay. I didn't emphasize it, but this is a quite common thing that if you just Google the chloroform and acetone, you'll find this this diagram. People try to explain it quite a lot. Okay, we can do the FTIR experiment, how the ketone peak shifted and so on, and that's something that we can do in the experiment. Okay, the Maxwell distribution of the speed. Okay, and then this is a speed distribution, and you don't have to remember this equation, but you want to know this one. Okay, so this is the term that was inserted because we are looking at the same speed without caring about different directions. So having this v square, we are differentiating ourselves from velocity versus speed. Okay. Without this is a velocity distribution, but now the speed distribution has a constant. It's actually 4 pi v square is the one that having the one with constant speed, regardless of the direction that you are pointing in the three-dimensional space. Okay, so then the question now is the calculate mean cubed speed. Okay, cubed speed means like this. And then if you, okay, what that means is this. Okay, and so therefore they want to use this distribution function and multiply by what you want to average them out. So that's the one. And then because the v is 0 to infinity, so this will be the answer. For that, okay, and so this cannot be true because that's for the velocity can go back and forth any negative value, but speed wise we only care about the magnitude, so that's why this is a speed. Okay, so there are two reactions with an activation energy and pre-exponential factors. Looks like an Arrhenius equation now. So reaction rate is an A exponential 2 activation energy divided by KT or RT. So that's the one. And then the say the reaction rate constant for reaction 2 is always greater than that for reaction 1. That means K2 is bigger than K1. K2 is bigger than K1. So to make that happen, either A2 is bigger than A1, and actually this is a negative term with activation energy. So activation energy for 2, activation energy for 1. Which one is bigger? This one. So activation energy is something more like, resisting force, right? This is an activation energy. So if you have an activation energy is smaller, the reaction is much easier to go over through this activation energy barrier, right? So, okay, so A2 is bigger than 1. And then A2 activation energy is smaller. So the B is the correct answer. Okay, number 33. So the curve representing molecular speed distribution for different gases at the same temperature. Okay, same temperature means same kinetic energy. Right? Kinetic energy is half times mv squared. So if m goes up, your average velocity is coming down. So species with the largest molar mass. So this is the heaviest one. So A is the correct answer. This here. We have almost come to the end. So very good. This is a problem set I discussed in my YouTube video before throughout my discussion with you in the last previous class on the kinetics. So consider this consecutive elementary reaction. The steady state approximation is using for the component B. So there are two things about steady state. Steady state approximation. Steady state. I think that my hands are like electrostatics. I need to bring this one. Okay, steady state. And that means intermediate concentration does not change over time. That means it's steady. The second one is intermediate concentration is not so much compared to your original concentration of A. And so, this is a B is bigger than A, so bigger than A. So that's not good. This is pretty comparable. That's not good. Those are not good. So only this one is what is truly representative as a So this is a constant B at if you weigh sufficient enough, and then this A value is bigger than B value. So that's why this is an A value. Number 35 is the last problem on regarding the macro PChem component. And then this is probably the easy one for you. I hope you guys can do. The first order reaction. So what you mean by that is the rate for change, dA dt, depending on K with the first order. So this is the one. And that's a separation of variable. So this is a dA over A is a K dt. Right? So separation of variable, how to solve the differential equation. And so this one is now ln A over A naught is minus K T. So this is an answer. And you can find the expression for this is the differential equation. A is A naught at time equals 0, and that is also the notation. So having said that, what that means is ln A versus T. Right? And so that's the relationship. And if k value is positive, and this is the slope is minus k value. So D is the answer for this question. I think that's the end of my first set of the previous problem set. And then I hope this one was good running through. And it is a good idea for you to run through, and with starting from the blank piece of papers and trying to see if you can solve this problem. I mean, I tried to give an explanation, but when you read a problem, you can solve it in a quick way, and you can improve your standard test skills, and that's one of the, I guess, the reason that why you're taking this for these courses. Okay, so thank you for your attention. Let me